All right, so last night was due the assignment from section 1.8 and the web assign assignments for sections 1.7 and 1.8. So I'll have the assignment from 1.8 graded for you as soon as I can today, and I'll have a section assignment posted for section 2.5 after class. So I'll get that together and have that posted for you. And you can just get the info from the website, of course. Um, oh yeah, tonight is due 2.1 as well. So please, take note of that and make sure that one gets done for this evening. All right. So yesterday, did I start that? Yeah. We were talking about section 2.3 about various types of information that you can get when looking at the graph of a function. So first of all, the curve in the xy plane represents a function when it passes the vertical line test. Every vertical line crosses it at most one time. And the domain of the function is the parts of the x-axis that are vertically above and below or below the graph of that function. The range is the parts of the y-axis that are horizontally to the left or right of the graph of that function. So this function has domain 3 to infinity, range 2 to 6. Couple examples of that there. Then we talked about intervals of increase and decrease. Right? When the function's going up from left to right, that's an interval of increase. When it's going down from left to right, that's an interval of decrease. Given these functions, the graph of this function here, you can see these intervals of increase and decrease. And the parts where they change from increasing to decreasing, that's called the local maximum. And decreasing to increasing, that's called the local minimum. And then the third thing that you can get is solutions to equations and inequalities. So if you've got this function here, so the same one that we had in the previous example, and the function f of x was defined algebraically in some way, and so we look at the equation f of x equal to 0, and what are the solutions to that equation? Well, if you have the graph in front of you and you know where they cross, the graph crosses the x-axis, well, the value of the function is the y value, and the y value is 0 when you cross the x-axis, when you're left or right from the origin. So the solutions to the equation where the value of f of x is 0 are just where we cross like that. So, or not necessarily cross, but intersect. So let's actually change that a little bit more. You could also have something like this, not necessarily cross, but just touching. So we'll say that's point positive 4. Right, so the solutions to f of x equals 0 are those points where the graph touches or crosses the x-axis. If you've got two functions, graphed simultaneously, what y equals f of x and y equals g of x, right? The places where they cross are the solutions to the equation, not cross, but the places where they meet are the solutions to the equation y, or not y, but f of x equals g of x. So, for example, so here is that standard parabola y equals x squared. And here is the line y equals x plus 1. And we see that there's two spots where they meet, right? So if this is the x-axis, that's the y-axis, and we're interested in what these points on the x-axis are. Well, they are the solutions to that equation where x squared equals x plus 1. So point A, point B. Right, so what are A and B? Well, they are solutions to x squared equals x plus 1. Right, they're where the y values of those two functions are the same. Right, that where the y values of those two functions are the same are going to be the points above the x-axis that are solutions to that equation. Okay, so let's solve this equation. So it's a polynomial quadratic equation, so we move everything to the right. This polynomial factors, it is x minus 3 times x plus 2. Right, so x equals 3 or x equals 2. So there you are, or negative 2. That's A and B. Right, so A is equal to minus 2, and B is equal to 3. So consequently, you can also get solutions to inequalities involving f and g, right? The points at which, say, g of x is greater than or equal to f of x are the intervals along which the function of g is above the function of f. So also, to the inequality g of x, not where it's equal to f of x, but where it's bigger than or equal to f of x, are the intervals for which the graph g of x is above the graph f of x. The graph y equals g of x is above the graph y equals f of x. So again, in this example here, so we already know what those points are. This is -2, and that's 3. All right, we see that x plus 1 is greater than or equal to x squared when -2 is less than or equal to x is less than or equal to 3. All right, so -2 to 3. Or if you wanted to know where x squared is strictly greater than x plus 1, that's when x squared is above x plus 1, right? X plus 1 is above x squared between -2 and 3, and outside of those two, outside of that interval from -2 to 3, x squared is above x plus 1. So x squared exceeds x plus 1, so that's when x is less than -2, this time strictly less than, or x is strictly bigger than 3. Right, so on the number line, looking like this. There's -2, there's 3, and these two intervals here. Okay, so knowing what the graph of a function is and what it looks like tells you a lot of information about the function. Not that you can always get really an accurate picture of uh, the graph of a function. Sometimes you can, a lot of times you can't. So let's take a look at some of the problems in this section. So that was section 2.3. So we got here 7, 9, 11, 15, 31. 7, 9, 11, 13, 15. So problem number 7. Let's take a look at that there. So just a simple picture of a function, and the picture of that function is presented on a square grid. So when you've got that square grid for your xy plane, you can tell something about, it's easier to tell what the x and y values are for the points that the graph goes through. So in this picture, what do we got? We've got, you have to, if you can look at the book, let me pull up the, it's going to take me a while to pull that up. If you look at your copy of the book, it shows you a point at -3, 3. So again, it's a function that has like this hard stop at that solid dot. And then it doesn't go through any of the grid points except for, what point is that? That point is -2, 1. So here's 1, 1, 2, 1, 2. So it goes through this point, and then it goes through this point here. So it does like that. And then it crosses the x-axis again, but it doesn't really sort of tell you. It's just slightly to the right of the 1. Then it goes up to this point, 2, 3. So 1, 2. To this point here. And then 3, 4. So it goes like that. And then it comes down 1 and stops. So all of the points that I'm emphasizing with these dots, those are points that where the function definitely goes through the grid lines shown. So this is 1, 2, 3, 4. And this is y equal to 3, y equal to 4, y equal to negative 1 right there. Other than that, it doesn't, doesn't really show it passing through any other grid points on the graph paper that it's shown on. And then it asks you various questions about that graph. A, find h of negative 2. Oh, and this is y equals h of x. It doesn't say that, but that's what it is. So h of negative 2. Right, so here's negative 3, here's negative 2, obviously, and that's negative 1. Right, so h of negative 2 is what? So for x value negative 2, what is the corresponding y value, if this is the graph of that function?
1.
1. B, domain and range. So domain is all of the x values above and below the graph. So this is minus 3 to 4. Range, all the y values left and right from the graph. So that's minus 1 to 4, including the minus 1, including the 4. D, or C, find the values for which, so solve h of x equals 3 when x is equal to what? So h of x is equal to 3 at, so here's the line, y equal to 3. All right? That's the line y equals 3. So where do we touch that line with the graph h of x? Where is h of x equal to 3? Which x values?
Negative 3, 2, and 4.
Negative 3, 2, 4. Okay. D. H of x is less than or equal to 3. So this is the function f of x equal to 3. So just that constant function 3. So h of x is less than 3, so below the 3, where? On which interval? Where is h less than 3? Where is the graph below? Well, from minus 3 to that point there, 2. So from minus 3 to 2. That's where we're below 3. H of x is bigger than 3 from 2 to 4. E, the net change. Oh, they cover, I thought that's the next section. The net change. Okay, well, let's cover that briefly. Given a function f of x and an interval a to b in the domain, okay, so they call it in this book the net change, or it's often called total change as well. The net change or total change of f of x on a, b is, well, it's just f of b minus f of a. Okay, of course, that's not a very sort of useful measure because, I mean, the net change could be 0, like this function here. The net change of h from minus 3 to 3 is, well, it's h of 3 minus h of negative 3. Well, h of 3 is 3 minus h of negative 3 is 3, which is 0. So here, the net change of that function is 0, but that doesn't mean the function hasn't done anything. Just, we ended up at the same place that we started at with the function. So that's the net change. Number 9, they're giving you two functions, f and g, in the graphs, in the picture. So let's see, g does something like this. Nope. G does something like that. F is doing something like this. So this is y equals fx, y equals gx. And you can see where they cross on these grid lines. That is the point -2, 1 right there. Let's see if I get in there and label it. So this is the point x value -2, y value 1. So this is -2. This is value 1. And this point right here is 2, 2. So x value 2, y value 2. And it asks you several questions. A, which is larger? F of 0 or g of 0? Well, the larger one is, so that's the x-axis, that's the y-axis. The value of the function f and g is on the y-axis. And at 0, that's at the origin, the larger one is this one here, and that's f. Right, so f of 0. Right, so f of 0 is like 3, and g of 0 is 0.75 or something like that. Which is larger, f of -3 or g of -3? Well, -3 is right there, and you see that g is above f. See? solve fx equal to gx. What are the solutions to fx equal to gx? Now, fx and gx, the graphs cross, right, where their y values are the same. What you're interested in is the x values, where they cross. Those are the solutions to the equation. So this is equal to -2 and 2. Okay, you're interested in the x values. X equal to -2 and 2. D, f of x less than or equal to g of x. Well, that's between -2 and 2, where f is less than g. So this is -3 here, and I didn't draw this good. Oops. So this should somehow these graphs would start and end in the same place. So this is x equal to -3. This is x equal to +3. So where is f less than g? Well, that's from -3 to -2. Union 2 to 3. Right, that's where the graph of f is below the graph of g. And E, solve fx is strictly greater than gx. Well, that's where f is above g, so that's inside the interval from -2 to 2. Not including the -2 and 2, because that's where they're equal. Okay, so basic sorts of observations you can make about a graph. 7, 9, 11, 15. '31. We talked about 31. That's just about passing the vertical line test. Now, what did we assign in this section? 8 and 44. Yeah, that's just finding local maximums and minimums. I mean, so number 44, where are the local maximums and minimums? So let's look at 43. So for number 43, we have the graph of a function that looks like this. So, and you can tell from the picture where these points are. So this is 2 on the y-axis. This point here is 2 on the x-axis. These points you don't know, but this is -2 on the x-axis. And use the graph to estimate the following. So A, local maximums and minimums. So local maximums and minimums occur at x equal to, so you got a minimum at -2, a minimum at 2, and where's this maximum occurring? So when you say a local maximum and minimum occurs at a certain place, the occurrence is the x value. Okay, so where's the x value of this maximum? I got minimum here, x equal to -2, x equal to 2. Where is this maximum occurring? What is the x value where it's happening?
0.
At 0, yeah. -2, 0, and 2. All right, the values of the local maximums and minimums are, so you can tell this one, it's at -1. This one, oops. This is at -1. So the values of the local minimums are as follows. The minimums have values -1 and 0. All right, that's the y values of the minimums. And the maximum has value 2. All right, so the occurrence of local maximums and minimums are the x values. Let me actually write that down. Y equal to -1 and 0, and y equal to 2. And the maximums, or sorry, and the values of the maximums and minimums are the y values. B, the intervals of increase and decrease. So intervals of increase and decrease, that's, separated by the maximums and minimums. So the function is increasing on the interval from -2 to 0. Usually you don't include the maximums and minimums as a point where you're increasing or decreasing. So that's kind of a point where it stops, where the function kind of stops and turns around. So it doesn't belong to the increasing interval nor the decreasing interval. So from -2 to 0, and then from +2 onwards. And decreasing from -infinity to -2, and from 0 to 2. All right. So just some various, just sort of vocabulary and terminology that goes along with functions. That's, has general usefulness when you're talking about such functions. So the next section is sort of a preview of ideas that are used in calculus. Well, sort of the central idea in calculus is the following. It's about rates of change. So average rates of change. Now, in practical terms, the average rate of change is not that useful a measure. It is a useful measure in some instances, but not that useful. What is really useful is the notion of an instantaneous rate of change. And we talk about instantaneous rates of change all the time, especially when we're driving or we're bicycling or we're running or walking or whatever the case might be. Well, I'm walking at 4 miles an hour, right? That means my rate of change of distance walked is 4 miles per hour. Not that doesn't change, right? I'm 4 miles per hour and I'm feeling good and I get it up to 4.5 miles an hour. And then I get tired and I go down to 3 miles an hour or something like that. Or when you're driving, of course, your speed changes all the time. 30 miles an hour, 65, 70 miles an hour, so on and so forth. So given a function f of x and an interval usually a closed interval, in its domain, the net change, usually called total change, of f of x on the interval is f of b minus f of a. Right, like we were saying in the in the homework for the last section there. Right, so f of b minus f of a. So the right hand, the value at the right hand endpoint minus the value at the left hand endpoint. Okay, so the value where you end up minus the value where you start. The average rate of change. So again, the instantaneous rate of change is the sort of really useful measure, but that's what requires calculus to define what that actually means. I mean, intuitively, we're all kind of like used to the idea of an instantaneous rate of change. But the mathematics of it is a little bit more complicated and requires, some further notions than what's available in just algebra. It's nothing too complicated, of course, but, something that needs to be talked about. So the average rate of change of f of x on the interval is f of b minus f of a over b minus a. So average rate of change, and so total change over the length of the interval. Graphically, it looks like this. These quantities are as follows. So you've got your function y equals f of x. And here's a. And here's f of a. And then we'll put b right here. So that's b. This is f of b. Y equals f of x. Now consider the line that goes through both of those points. Alright, so the total change is this length right here. So total change, or net change I guess they're calling it. The net change is this length right here. And the length of the interval from A to B so length of the interval AB is right-hand endpoint minus left-hand endpoint B minus A. No need for absolute values there because we know the B is to the right of the A. And the net change is, f of B minus f of A, and that's that. length right there, and then the slope of the red line that connects those 2 points is the average rate of change. So that's the rise, f of b minus f of a, over the run, b minus a. All right, rise over run. Total change divided by the length of the interval. So that's the average rate of change. So, for example, let's write f of x equal to x times x minus 2 times x minus 4. The average, so find the average rate of change from x equals 1 to x equals 4. So the average rate of change from x equals 1 to x equals 4, so the interval from 1 to 4, that's f of 4 minus f of 1 over 4 minus 1. Okay, no big deal. F of 4 is, of course, what? What's f of 4? Right, since this is x minus 4, it's 0 minus, well, f of 1 is 1 times minus 3 over 3. So this is equal to 0 minus, and then the product inside here is positive 3. So it's just 0 minus 3 over 3, so it's minus 1. So minus 1 indicating that the function has decreased over that interval from 1 to 4. So since the average rate of change is negative, the function f of x has decreased in total from, well, on the interval from 1 to 4. And if you graph that function, not that we've talked about how you can graph such a function, although it's not really a big deal, to get a rough sketch of it, this thing is equal to 0 at 0, 2, and 4. 0, 2, and 4, and then aside from that, it's going to do this. Something like this. Not that. Oops. No. Incorrect. It's going to do like this. Now, why it does like that, we'll talk about it later. Although, really, the information that we have so far pretty much indicates that that's how this function behaves. So we see that, like, f of 1, not that that's where the local maximum is, although the way I drew it is sort of implying that, but where that local maximum is less clear. But anyway, what we've got right is that, so this is slope -1, this line. is sloped downwards. So from 1 to 4, the function has in total decreased. Right? Not that it's always decreasing. I mean, it's increasing at some point here between 2 and 4. It's increasing, or no, we're starting at 1. Yeah, it's decreasing from here to wherever this local minimum is, and then it's increasing from that local minimum to 4. But in total, it has decreased. What did I want to say about that? Oh yeah, where those local maximums and minimums are occurring, that requires calculus to find where those things are actually happening. But for now, we're not going to really talk about that in this course.
Where did the 0 come from?
Oh, well, where is this function equal to 0? At 0, 2, and at 4, right? It's a polynomial in factored form. So when you have the polynomial in fully factored form, you just look at it and we see where the zeros are. It's where this is 0, or this is 0. Right? Other than that, it's not going to be 0. Right? If this is not 0, this is not 0, and that's not 0, the product of a bunch of non-zeros is always non-zero. As a matter of fact, we also know within those intervals where it's not 0, whether it's positive or negative, right? So before 0, right, so for x equal to -1, say, this is negative, negative, and negative. The product of 3 negatives is negative, and that's what we've drawn. Between 0 and 2, at like 1, this is positive, negative, and negative. So the whole thing is positive, which is what we've drawn. Between 2 and 4, it'll be negative, and from 4 onward, it's going to be positive. So we know the graph kind of looks like that. What we don't know is where these relative maximums and minimums are occurring. And also there's these changes in concavity from concave up to concave down, which I've sort of indicated here, but we don't actually know that that's where it's happening. But those finding out those points where the curvature is changing, that requires calculus. All right. So rates of change and units of measure. So when a function f of x is measured in some units, call them p, p, and x is measured in units q. So, f of x is p, I don't know, p being miles, and x is hours, right? So the function f is in miles, distance traveled, x is in hours, time traveled, or something like that. The average rate of change is measured in, well, what is the average rate of change? It's f of b minus f of a over b minus a. So in units of p over units of q, which is read as units of p per unit of q. Right, so miles per hour, miles per second, meters per second, dollars per unit, or dollars per widget, or dollars per hour, or whatever units you're using here. Gallons per minute, like when you're pumping gas, you're interested in how much gallons per minute is pumped out of that gas pump. so on and so forth. So that's all they're really talking about in section 2.4 are just these average rates of change and what the units for the average rate of change are. So in the last 10 minutes, let's see if we can't get into section 2.5. And section 2.5 relates the ideas of section 2.4 to linear functions. So why don't we do that? So section 2.5 is on linear functions. So we've talked about lines and equations of lines already. But now we're going to talk about functions, which essentially are given by graphs of lines. So it's kind of the same thing again, but we're going to talk about rates of change and examples that use these rates of change. So definition of function f of x is linear when it is of the form f of x equals a times x plus b, or we'll put an m there. M of x, m times x plus b. So for example, f of x equal to, well, let's use a different letter even. F of t equal to t minus 2 over 3, right, is linear. You can rewrite it as 1/3 of t minus 2/3, right? Distributing the 1/3 over the t minus 2. So m is 1/3, b is minus 2/3. F of x equal to, let's say, x squared minus x times x minus 2 plus 1 is also linear. You can rewrite it be rewritten as follows. I mean, a linear function shouldn't have an x squared in it. It's supposed to be m times x plus b, where m and b are constants. M and b are constants, but x is the variable. So it shouldn't have an x squared in it, but this function can be rewritten like this. So x squared, distribute the x through here, and you get minus x squared plus 2x plus 1. And lo and behold, those go away, and you get 2x plus 1. Right? So that is linear, where the m is 2 and the y is 1. Okay? Here, m equals 1/3, y equals minus 2/3. The slope of this linear function, right, the 2 in this case, the 1/3 in that case, the m value in general, right, with the line we call it the slope. So given any interval f of x equal to mx plus b, and any interval a comma b for x, the average rate of change of f of x on that interval is always just the slope m, right? Because I guess I shouldn't use a and b here. Interval, let's say p and q, the rate of change is always just the slope m, no matter what that interval is, right? Because f of p minus f of q over p minus q is equal to, well, f of p is m times p plus b, minus f of q, well, that's m times q plus b, over p, or q minus p, excuse me. Oh, I did this backwards, didn't I? f of q minus f of p over q minus p. So this is mq plus b minus mp plus b. So mq minus mp plus b minus b over q minus p. So these go away, and we can factor out an m here. So it's m times q minus p over q minus p. So those cancel, and you just get m. So that average rate of change and the slope, right, those two ideas coincide with linear functions, right? I mean, and geometrically, of course, that makes plenty of sense, because the average rate of change is supposed to be the slope of the line that connects the 2 points of the function for which you're using to measure the average rate of change. When the function itself is a line to begin with, the line connecting 2 points on the line is just that line, right? So it's easier to see it geometrically. If you take a line and 2 points on the line, then the line connecting those 2 points is the same line, right? And the slope of that, that slope of that connecting line is the rate of change, but that's the original slope. But algebraically, you can see it works out as well, as it should. When the geometry tells you something is true, the algebra should say the same thing, and vice versa. Okay, so let's look at some problems dealing with linear functions and rates of change. Remember, when the rate of change is stated as units of p per unit of q, right? When the rate of change is stated as rate of change of f of x, is given as units p per unit q, and well, then the function, right, is given as unit p per unit q with value m. Then we know the function has the form f of x equal to mx plus b. Right? We'll know what the m is, and then, we need to figure out what the b is. Okay? And sort of the part of a problem that gives away that it's a linear function is when you say the rate of change is constant. So when the problem, we have to finish up, somehow says the rate of change is constant. So, you're driving at a constant speed of 35 miles per hour. Or, water is running out of a hose at 2 gallons per minute. Right? If that rate of change is stated in some way, implying that it's constant, then you're dealing with a linear function. If a rate of change actually changes, then it's not going to be a linear function. Right? So, you're accelerating from 30 miles an hour to 60 miles an hour. So, in this case, the rate of change is moving. You're speeding up. Or you're decreasing in speed from 60 miles an hour to 30 miles an hour. Your rate of change is going down. It's decreasing. Right? But if somehow the problem states that the rate of change is constant, you're simply dealing with linear functions. Okay? So we'll do some examples of this tomorrow. Please don't forget about the assignments that are due today, and I'll send you an email after class updating you on the assignment for section 2.5. Okay, have a nice day, everybody. I'll be in my have office hours in WebEx. 12:30.